And the next speaker is Haruka Sakemi, who is going to tell us about particle cosmic ray acceleration in SS433. Thank you.
Okay, can you hear me?
Yes, perfectly.
Okay, thank you very much. Hi, everyone. Thank you for giving me a chance to introduce my work today. I will start with self-introduction. I am Haruka Sakemi. I am a postdoc at National Astronomical Observatory of Japan, and I will move to the Kagoshima University this October. And I got my doctoral degree with the study of microcrystal SS433 and the surrounding radio nebula W50, and also on their surroundings. And today I will introduce you to a part of the topics of the doctoral thesis. And as you know, the cosmic ray is a charged particle that has a very high energy and high velocity. And they are observed on Earth, and their energy distribution is roughly from 10 to 7 to 10 to 20 eV. And they occupy a large portion of the energy distribution of our galaxy and the local universe. And the origin of these cosmic ray particles is still under discussion, and especially in the middle range of the energy. There are many candidates sources, and it has been discussed for a long time. And recently, the X-ray binary jets are attracting the attention as a strong candidate to explain this energy range, and because of their scale size and even time scale and the population. And recently, microcrystal SS433 has received a lot of attention because GB and TB gamma ray emissions have been identified around SS433 and the W50. The W50 system, especially the TB gamma ray emission is located on the SS433 jet axis like this, around the X-ray lobe. And so the gamma ray emission should be related to the cosmic ray particle acceleration to high energy by the SS433 jets. And unfortunately, there is no radio emission around here. It is essential to consider how this region realize so low radio emission while X-ray and gamma ray are bright. And so many scientists focused on the TB gamma ray region as the accelerator of the cosmic ray particle. But in this study, in our study, we focus on the eastern edge region of W50. And there is a filamentary structure at the eastern edge, and the filament is believed to be formed by the SS433 jet as a terminal shock. So there is a possibility to happen the acceleration by diffusive shock acceleration around here. And in fact, although there is no gamma ray emission around here, but we found non-thermal X-ray emission around here. So we focus on this region in this study. And we would like to know whether galactic X-ray binary jets and the microcrystal jets can be a dominant accelerator above the 10 to 15.5 eV. So in order to reveal it, first we require to investigate the maximum energy of cosmic ray particles accelerated by the galactic jets. And hereafter, we investigate the maximum energy of cosmic rays accelerated by the SS433 jet terminal region based on radio observation. As a first step to estimate the maximum energy of cosmic rays accelerated by the SS433 jets, we assume the acceleration mechanism as a DSA, like this, and derived some physical parameters from radio observations. And so specifically, we derived the shock velocity and the magnetic field strength and the distance. And we used the VRA data observed in 1984, 1996, and 2017 to investigate the physical parameters of the SS433 jet terminal shock region. And the observed frequency is 1.465 gigahertz. And we made the spatial resolution of these observations even with 60 arcsecond. First, we investigated the magnetic field strength of the terminal filament on here, assuming the equipartition field. And we derived the value of 39 microgauss, assuming the equipartition. And also, we investigated the magnetic field structure on the terminal filament. And using the polarization data with the ATCL. And also, there is no time to explain the details today. We identified the well-aligned magnetic fields along the filament, and it implying the compression by the terminal shock. And next, we investigated the shock velocity. And note that we require some assumptions to derive the shock velocity by radio observation. In the case of strong shock and monochromatic gas, the shock velocity is consistent with the upstream velocity and 4 times of the downstream velocity. So we derive the downstream velocity directly by comparing the position of the eastern edge filament. And there is a previous study, Goodall et al., and they investigated the position change between the 1984 and the 1996. And however, there is no significant change, and they seem that these filaments seem to be stable. There is a panel, the right panel shows their result, and the yellow and black line shows the expected position moving during the 12 years, but the blue and the red and the green filaments shows the past observation, but these filaments don't show the move, and they seems to be very stable. And we added the newest observation and investigated the velocity of this filament with the 33 years. And here is the result. And assuming the upper limit velocity derived by the previous study, the filament should move easternward by 15 arcseconds from the position in 1984. So I mean, the filament should move about the 15 arcseconds from here to easternward with the 33 years. However, we revealed that the filament is still stable. So this panel shows a comparison of the filament in each observed year. And all filaments are overlapping. So there is no significant motion over the astrometric error. So we updated the upper limit velocity as 2.3 of the speed of light. And finally, we estimated the maximum energy of the cosmic ray particles accelerated by the terminal shock. And we assumed the propagated distance of the shock with this length correspond to the distance after the jet breaks through the shell. And using these values, we finally derived the maximum energy of 1.4 times 10 to 17 eV. And it is fully above the energy of 10 to 15.5 eV. And we also estimated the lower limit energy by changing the velocity like this. And we assume that the downstream velocity is corresponding to the sound speed of the plasma gas. And it was estimated based on the XMM Newton observation. And in that case, the maximum energy is 6.2 times 10 to 15 eV. And so, okay, thank you. So we can conclude that there is a possibility that the jet terminal shock can accelerate particles above the 10 to 15.5 eV. I summarize my talk. Recently, the galactic X-ray binary jets are focused as a strong candidate of dominant accelerator above 10 to 15.5 eV and below 10 to 18 eV. So we investigated the maximum energy of cosmic ray accelerated by the most famous microwave SS433, and we revealed that it could accelerate particles above 10 to 15.5 eV at the jet terminal shock if the energized jets is reaching at the eastern edge. Finally, I introduce our prospects. Recently, we carried the new observation of W50 at higher frequencies with the BIA. And we identified the radio emission around the TB gamma ray emission. The TB gamma emission from here, and this is the X-ray bulb, and we found some filamentary structure at radio wavelengths, and it seems very corresponding to the H-alpha emission like this. So we will work on the multi-wavelength study for the region from radio to gamma ray. Okay, that's it. Thank you for your attention.
Thank you. Do we have question? I don't see any on the Zoom. Do we have a question in the room? We don't hear you.
No, for the moment, no.
I see Mukesh Vyas has a question. Please go ahead.
Yeah. My question is a bit general. In the previous slide, you showed the spectrum of cosmic rays, but at high energies, we see it's not power law, it's some kind of bump is there. Do we have any picture for that?
Sorry, you mean
the spectrum at high, yeah. So at high energy, we see there's a bump, so it deviates from power loss. So do we have any picture or any understanding for that?
So you mean the upper energy region? So you mean the above the around here?
About 10 to the around 10 to the 19.
Ah, okay, 10 to the 19. So we didn't focus on this energy, but maybe it is very difficult to realize the such high energy to accelerate by the X-ray binary jets. So I consider that the main accelerator is, for example, the AGN jet or gamma ray burst, like this, such the sources, I think.
Okay.
Is it okay? Thank you.
Sorry. Any other question?
No question here.
Okay, so if there is no more question, we can thank the speaker again.
Thank you very much.